as we get down to the last two sections of the chapter, the first piece we want to talk about is the divergence theorem, sometimes called the Gast theorem. And it deals with the relationship between flux and the divergence. And just like with line integrals, the Green's theorem allowed us to take work and a line integral and use a double integral of the region. Well, now we have the divergence theorem that says that we have a solid region bounded by a closed surface. So we have a surface oriented by a unit normal vector directed outward, so coming out, right? Unit normal vector coming out. If F is a vector field, back to the first section, whose component function has continuous first partial derivatives, you can take the partial derivative. Then flux, the integral of the vector field dot product with the unit vector, normal unit vector, ds, okay, can be evaluated by the triple integral of the region, okay, the three-dimensional region, the divergence of f dv. Now the divergence of f we found out in the first section. We didn't use it, but we found it in the first section that it is the dot product of the partial derivatives with the vector value function. It's the dot product of the first derivative with the vector value function. And so sometimes this is the way we have to do a surface integral work, okay? And we need to use the divergence. And it turns it into a much easier problem. For example, use the divergence theorem. Let Q be the solid region bounded by the coordinate plane and the plane 2x plus 2y plus z equals 6. So the coordinate plane down here in the xy plane, and then we have the plane. So it's going through 3, 0, 0 when you look at this, and 0, 3, 0, and 0, 0, 6, right? And we're looking at this region bounded here, right? It's a solid region, and it's outwardly looking at a normal vector. Any normal vector would be coming out, right? So the solution, right, we're finding this integral, the integral of the surface, f dv dn ds. ds, again, is our problem. But the divergence theorem, we only need a triple integral. Okay? Now, again, if you were looking at this, you would actually have 4 surfaces: the bottom, the plane, and the 2-coordinate plane xz and yz. And you would have to find all of those. You have to find 4 surface integrals to evaluate this. But by the divergence theorem, because we have a vector field, so the derivative of x in relationship to x, the derivative of y squared in relationship to y, the derivative of z in relationship to z gives us 1 plus 2y plus 1 or 2 plus 2y. So this integral, this surface integral, can be evaluated using this triple integral of using the divergence, which would be 2 plus 2y. And then we have whatever order we want to do it in. And since the y is in here, I would do the y last. So z, okay, z is going from 0 to the plane. So from 0 to 6 minus 2x minus 2y. X, the x, right, again, we come back to here. If z is 0, right, then x equals 6 minus 2y divided by 2, or 3 minus y. And y is going from 0 to 3. So we take the integral from of 2 plus 2y, that's a constant. So that's going to be 2z plus 2yz from 0 to 6 minus 2y minus 2x minus 2y. So 2 times that is 12 minus 4x plus 4y. And then 2y times that would give you minus 4 minus 4y squared, minus 4xy minus 4y squared. And so we have that region all settled in here. Right? And then we've got this derivative in relationship to x, so 12x minus 2x squared plus 8xy minus 2x squared y minus 4xy squared from 0 to 3y. So you put that in and simplify it, pretty easy exercise to do. And then take the derivative relation to y, and we have just found the flux of that region. We've just found using the divergence theorem. Much easier than using some other way of doing it. Just to see that, let's verify here. Here we have z equals 4 minus x squared minus y squared, parabola. Okay. Sitting on the xy plane, we have the vector value function 2z I plus xj plus y squared k. And we want to verify that the divergence theorem works. Well, we have two surfaces. We have the upper surface oriented out and the lower surface oriented down. The lower surface would just be straight down, so the normal unit vector would be minus k. So f dot minus k ds. And then f dot in the outer surface, the integral, working with this integral and looking at f and n. So we can find n by taking the derivative here, right? And looking at it outward, so it's going to be 2xi plus 2yj, derivative plus k, 1k, okay, z is. Remember that was minus minus plus, but because it's going to be minus 2x, I think plus minus 2y, and then it's going to be minus z, which is 1, which is going to give you there, over the square root of the norm. All right, so 4x squared plus 4y squared plus 1 square root ds. So we take the dot product of these, right? And again, we would end up with f dot minus k. It's going to give me minus y squared, because that's the only, when we have the k parts here, the x parts. ds, well, this is area, because you're talking about the area down here. So it's the area of the region. The region is a circle. So that gives us our first piece. Then f dot, here's f, dot with this would give us 4xz plus 4xy plus y squared, dot product here. And then ds over the square root here is going to be dA of the region. And the region again is that circle down the xy plane. So we have the same integral, so we can add up the pieces. Right? So minus y squared with y squared, so we end up with 4xz plus 2xy dx dy. Take that integral, right? And the z is 4 minus x squared minus y squared. So now we're taking this integral, and if you take that integral and do the work, you'll find out it turns out to be 0. A lot of work to get there. On the other hand, okay, the divergence of f, okay, here's f, 2x, the 2zi plus xj, so you take the divergence, the derivative of this relation to x is 0, the derivative of this relation to y is 0, the derivative of this relation to z is 0, so this integral becomes the triple integral of the divergence, which is 0. Look how much easier the divergence theorem makes this work. The divergence theorem. The divergence theorem. When we want to do this integral of a surface that's outwardly oriented, okay, with a vector value function, I can use the divergence theorem. So the derivative in relation to x of the I piece is 2x. Derivative in relationship to y of the y piece is x. And the derivative relationship to the z is 0. And so we have the triple integral 3x dv. And because of the circles down here, x is r cosine theta, dv is r dv, dr d theta, putting it into cylindrical coordinate systems. So r is going from 0 out to the top of the base here, top of the top piece here, which is x plus z equals 6. So we've got r cosine theta, r sine theta, we've got z equals 6 minus x, which is 6 minus r cosine theta. R, it's our radius of our circle down here, so that's 0 to 2, and we're going all the way around from 0 to 2 pi. And so the divergence theorem makes this quite easy to do. Right? So quite easy to do. So to understand the divergence theory, consider the two sides of this equation. Okay? This is flux. This is the divergence theorem. This is flux, and this is the divergence theorem. And so if you think through that and look at what's going on there. My mistake, there we go. Now we have it for focus. Right. The flux of the function across the surface is the divergence of the function dv. Right. And so when we look at that, you're talking about a surface and you talk about a flow over it. Okay? That's what flux is. And it's interesting that if the divergence is positive, this guy is positive, right? Okay? You could think of it as a bump, and the water would flow away from it. We call it a source. When the divergence is less than 0, we can think of a sink, like a sinkhole. If it rains, the water is all going into it. And if the divergence is 0, it's flat. And so whichever way the flow is going, it'll just go. So again, calculate the flux. Okay, that's that integral. We've got a region, x squared plus y squared plus z squared equals 4. Find the outward flux of the vector field, 2x cubed I plus 2y cubed j plus 2z cubed k, okay, through that sphere. Okay? So that's the flux across the sphere. I can use the divergence theorem. So the divergence in relationship to x is 6x squared. The j component in relationship to y is 6y squared. The z component in relationship to z is 2z squared. So we've got, or 6z squared, 6 on all of them. So 6x squared plus y squared plus c squared dv of the region. Because it's a sphere, spherical is the easiest way to do this. Right? So we've got x squared plus y squared plus z squared. Right? Well, that's rho squared. And then dv is rho squared sine phi. So we get rho to the 4th sine phi. And we've got theta. And we've got phi. And we have rho. And you can look at it with either way you want to look at it. This is a good way to look at it because there's no theta in the first piece. So d theta is very easy. Theta is all the way around the circle of the sphere. So 0 to 2 pi. Phi is always from the positive z axis down And if a sphere goes all the way down, so it's going to be from 0 to pi, and the radius of our sphere is 2, so phi is 0 to 2, so it becomes a fairly easy integral to do. Fairly easy integral to do. So the divergence theorem. The divergence theorem is another way of trying to figure out what's going on here. Flux. Flux can be evaluated using the divergence theorem by applying what you see right here.